Says recording. All right. So welcome to the CUAHSI Virtual University Snow Modeling class. I'm trying to arrange my PowerPoints into modules where the first part will say the day. So this is day 1. And then I'm breaking the day into 3 parts. So this is module 1.1, which is logistics. The first part of logistics is this is a photo of Cale Martin programming in the snow. We will not have to do that in this class. So snow modeling does not mean running snow models while sitting in the snow. Before I get started, I want to say thank you to a lot of people who have been involved in helping getting this course going. Originally, this online class was inspired by a NASA summer snow school that was taught in June 2014 by Martin Clark, Bart Nyssen, Michael Duran, Glenn Liston, Drew Slater, Tony Rosati, and myself. One of the goals was, could there be something online after that? It's taken me 4 years to get there. And I also want to call out a special thanks to Bart, who's been working on translating those lessons into a purely online environment so everyone can actually do online snow modeling. I also want to say thank you to Liz Tran, who organizes all of the logistics behind the scenes for this. She's also organizing a 1-week in-person snow measurement class. If you're interested in digging in real snow after all the modeling, you need to apply by October 15th. Here's a link. I also want to thank all my students who have taught me and continue to teach me more about snow modeling. If there are any errors along the way, I take full responsibility, and I will try to acknowledge sources from people who've helped me with specific slides. So in acknowledgements, this is a slide put together by Mark Rowley when he finished his PhD dissertation. And he posed the question, how do we know what we think we know about snow? And so, he started with a picture of, most of us are interested about snow because we've gone outside at some point in time, and we've looked at it and we see reality. There's snow somewhere in a mountain. We want to know something about it. But how do we know about reality? So we can go out and make ground observations. And so here's a picture of somebody taking a snow course measurement, weighing the snow course in the snow. Next to it is a picture of a weather station that we put out in the snow. You can see that snow is not so good for weather stations. This particular one got buried and bent. But we have things that record the weather around the snow. We have a lot of satellites in space, remote sensing. This is a MODIS image of the Sierra Nevada. And you can see, snow is bright and white. We can generally see where snow is with remote sensing. And then, the focus of this class, we have snow models where we can try to represent what's happening in the snow through some kind of set of equations and simulations. Now, each of these represents some aspect of reality, right? Ground observations, remote sensing are directly looking at reality. However, there's some uncertainty in both of them. Ground observations, we never have enough measurements. When somebody goes out and takes the measurement, there's a lot of sources. If you go out and try it yourself, there's possibilities for measurement error. This poor weather station in the corner probably is not recording a very accurate snow depth right now. There's also a lot of spatial variability in the snow outside. And just a few measurements don't represent everything that's out there. Remote sensing looks at everything, but is often blocked by clouds. It's blocked by the forest canopy. And to get more than just presence, absence of snow, there's often some kind of retrieval algorithm that has its own modeling and set of assumptions built in. Now we have these, and these both give us the forcing for our snow models, where it tells us, what the weather is, what our, how much snow fell out of the sky for us to start modeling the snow. And then once we have that, our snow models themselves have, model parameters, model structure choices we have to make within the snow model. And then when we're trying to figure out whether our snow model is correct, we again are, left with these 3 things. We have ground observations, remote sensing, and each of them can give us partial confirmation, but not everything. So part of our goal is to try to be as thoughtful and do as much detective work as possible to figure out if our models are doing what we want them to do for the right reason, and giving us answers that help inform us about our ultimate goal, figuring out reality. In addition to all of this, there's scale issues at every step of the way. What scale are you running your model? What scale is the footprint of your remote sensing instrument? And what scale do your ground observations stretch over? The other thing we'll be talking about, this is a slide from Martin Clark, is the method of multiple working hypotheses. When we're trying to answer any question, basically what T.C. Chamberlain said is that scientists often develop parental affection for their theories and their models. And so most people, if you ask, why are you using this model? It's because my advisor used this model, or someone I knew used this model and they handed it to me, and therefore I used this model. Whereas effort is to bring in multiple working hypotheses. So if we could have a multiple modular framework, or if we could think about, as Chamberlain wrote in 1890, every rational explanation of a new phenomenon, the investigator then becomes the parent of a whole family of hypotheses, and by his parental relation to all, he is forbidden to fasten his affections unduly upon any one. As example, my older son likes to always ask me whether I love him more than my younger son. And because they're both my children, I can never say I love one better than the other, regardless of how they're behaving that day. So our course goals and objectives, we are going to be looking at the components of a snow model, so it's not a black box. We're going to talk about how to make decisions in constructing or choosing a snow model. We'll talk about how to run a snow model and test hypotheses using a snow model. We'll then go into how to calibrate and evaluate a snow model, and then critical thinking and detective work for any model. So the schedule today, Wednesday, October 3rd, we're going to go over an overview of the class and snow modeling. If you can get on the Canvas site, you should see the assignments for the first reading assignment and for a research profile, which I'll go over a little bit more today. And then over the next 7 meetings over 4 weeks, we will move on to all of the other aspects of the class. So let's start. This is a new system for me. So you should be able to see me in my video. Let's see if other people can turn. So you should have muted yourself. See if you can turn yourself on. Say hi, say your name. If you can turn on your video, you don't have to leave it on, but just turn it on so I don't feel like I'm talking to myself.
It says that you have to allow us to turn on our cameras.
I can allow you to turn on your camera. Okay. All right, just try talking. I could hear you. Try turning on.
My name is Jeff at Kent State University, master's student, and Jefferson is my advisor. I'm studying isotopes and looking at the isotopic composition of lake effect precipitation for Northeast Ohio. That's all I got.
Sounds good. Thank you.
Hi, Jessica. This is Friedrich and Michelle.
Hi, Jessica.
Hi, Friedrich. Hi, Michelle.
We're PhD students starting first year here at UW in civil engineering, and I'm looking at the glaciers of the Pacific Northwest, doing some mass balance and time series reconstruction.
And I'm looking at snow, annual changes over time, and we're both working with David Sheen.
Okay.
Hello, my name is Tim Yoder. I'm a applied math master's student at University of Washington as well. I'm an online student currently, working full-time currently as a HVAC engineer. but since I'm trying to change into the applied math field, and I thought this course looked very interesting, and it is my elective.
Excellent. I call it people. Ava Cooper.
Hi, I'm Ava Cooper. I'm a second-year master's student at the University of Nevada, Reno. I'm studying with Dr. Adrian Harpold, and I look at vegetation water use under different spring snowmelt conditions.
Excellent. Nice to meet you, Ava. All right, and I think I'm, sorry. And then we have Benjamin Serpa, and I think I may be able to allow you to share your webcam. You can try. I'm allowing you. There you go.
All right, cool. Hi, my name is Ben Serpa. I'm a first-year master's student in hydrology, also at University of Nevada, Reno. I'm working under Dr. Scott Tyler, and I'm doing a project, or I'm continuing a project that looks at the hydrologic impacts of forest thinning practices on the Lassen National Forest.
Excellent. And then Cassie Lambrazo, and it looks, you don't seem to have an option to have a webcam, Cassie. I'm not sure why. Can you talk? Hello?
Okay. I don't know what's wrong. Oh, there we go. Can you guys hear me?
I can hear you. Mm-hmm.
Excellent. All right, well, my name is Cassie, and I am a first-year master's student with Jessica. I am looking at snow inception.
Excellent. And then Devon, you also for some reason don't have a ability to share your video, but you should be able to talk. Maybe. Okay, Devon will work on unmuting. We heard from Friedrich and Jeff. How about Josh?
All right, do you have me?
I can hear you. I don't know.
Okay.
You don't seem to have video, but that's okay. You can talk.
Yeah, and I don't have the video option, but anyways, yeah, my name is Josh Jerdevin. I'm with Ava here in Dr. Adrian Harpold's lab. First year master's student, just began this summer, and I'm studying snow drought and the effects on stream flow generation in the American West.
Excellent. How about Devon? Can you, any success? You can also try typing in chat if chat is working and audio is not working. You can type some message. How about Juan Pablo Dominguez?
Yeah. Hi, can you hear me?
I can hear you.
Yep. So yeah, I am Juan Pablo. I am a first year master student at University of Delaware. Yeah, I have just started, and I will be doing hydrology in the Andes Mountains in Argentina. Is the place where I live.
Excellent. And Justin is sitting here, so he should talk on my audio. I'm not sure where my camera is.
That's it. Hello, everyone. My name is Justin. I'm here at University of Washington, and I'm mostly working on model representation of liquid water percolation and taking this one step further to take a look at glaciers and then more widespread observations of LiDAR snow depth.
Excellent. And Liz, do you want to say hi?
Oh, hi everybody. My laptop's closed, but I'm from CUAHSI, so you've been getting all the emails from me. So feel free, if you have any technical difficulties, whether it's GoToTraining or Canvas, feel free to shoot me an email or message through Canvas as well.
Excellent. Thank you, Liz. And Lewis, I think you can share your website.
Yeah, hi everybody. My name is Louis. I'm an incoming PhD student at the University of California at Santa Barbara, and I will be studying with Naomi Taig, who's actually teaching the next month's module on modeling R. But I will be working with her on modeling wildfire effects on the eco-hydrological cycle, as well as doing some snow hydrology assimilation for a fellow PhD student. Thanks.
And Scout, it looks like you can't do video, but you can hopefully do audio.
Hi, Jessica.
I can hear you.
Hi, okay. Hi, everybody. I'm Scout. Yeah, I don't see the option to do a video, but I can talk. I'm a master's student at the University of Washington, and I'm excited to model snow.
Excellent. And Stephen, you should be able to share video.
Yeah, I think I figured out the video. There it goes. Yeah, hi everyone. I'm a second-year grad student at University of Washington. My research is focused on scale issues with remote sensing.
Excellent. Thank you, Stephen. And Kim, hopefully you can do audio. You don't seem to have video.
Hello, can you guys hear me? I said hi already again, but I'll say hi again.
Thank you.
Timmy Oder.
Excellent. And then Devon is sent us all a text message that he will talk to us next time when he's at home and where he's not in his office and needs to be quiet, I guess. And Zoran, I think you can share webcam or talk.
I'll just talk.
Okay.
Hi, everybody. I'm Joran. I'm a first-year PhD student working with Dr. Erkan Istanbuloglu at University of Washington Civil and Environmental Engineering Department. I will also work as an earth scientist at Pacific Northwest National Lab. So my work relates to hydrologic modeling of watershed science, and also I'm currently doing some integrated modeling of hydrogeomorphic hazards projects at University of Washington.
Excellent. Thank you. And Bart, did you want to say hi?
Sure. So I'm Bart Nysen. I'm at the University of Washington, where I work with Jessica, and I'm helping out with the actual online SUMA simulation. So I'm sure I'll be talking to some of you in the chat channel on Canvas.
Yep. Did I miss anybody? All right. And all right. And Devon is working with Adrian Harpold, and hopefully I didn't pronounce her name wrong. She can call me later if she wants to clarify. Okay, so apologies for all of the slow start here. Let's go back to some logistics and then we'll move into the more science. Friedrich says that it's Devon. Thank you, Friedrich. All right. So, and I can see chat, so feel free to chat questions. I think you can also raise your hand, but I'm not sure if I'll notice. I think I'll notice chat before hand raising. So go for a chat. All right. Also, I've got up here, my phone is sitting next to me and will ring in the middle of this. So if all else fails, go ahead and call me. If anyone who's not in the class calls me, I'll just hang up on them. Okay. All right. So your first assignment is both a research profile and a prep for your homework assignments. The prep for the homework is labeled homework 0 in the Canvas. So the first thing is just the research profile, because as you can see going around and just having everyone say their name is a little bit awkward in the virtual world still. I think we should use the Canvas discussion board to get to know each other better. So please, over the next couple days, just in the discussion board, post a few sentences about yourself, what you do, what university you're at, what sort of research you're working on, and what you plan to do with your work in the future. And then read other students' entries so you have an idea who the people are. This class gives us a great opportunity to get to know people from other universities we wouldn't otherwise. This will also help me know where people are coming from as I develop the rest of the lecture slides so I can target it to the audience of who I have here. After people have posted on the discussion board, then please, just for an assignment to upload in the assignments on Canvas, just write a short 1/2 to 1 page answering questions. Basically, you can paste the same exact thing you pasted in the discussion board, along with what you hope to get out of this class. And then just to show that you looked at what other people posted, you know, who might you be talking to from other universities, both who might help your work and who might you be able to help. Homework 0, thank you to Bart, steps you through how to set up accounts on HydroShare, GitHub, and on the basics of Python with Jupyter Notebooks. Now, if anyone in the audience is like me, this sounds a little bit overwhelming, but let's do a quick survey. And here we can try raising hands. And let's try clicking on the hand raise of how many people have used HydroShare before. Click on your little hand icon if you have used HydroShare before. Bart raised his hand. That's good. All right. Justin's used it. So not many people have used HydroShare. All right. So who has used GitHub before? All right, we got a few more. Ava, Bart, Cassie, Devin, Friedrich, Josh, Justin, Lewis, Scout, Stephen, Tim. Excellent. I'm reading these because, again, on your homework of who might help you, people who have used these things before might help you. Okay, who's used Python before? All right, great. Tim, Stephen, Lewis, Justin, Josh, Friedrich, Devin, Cassie, Benjamin, Bart, and Ava. Okay. And then finally, I'm guessing it's going to be similar people using Python, also using Jupyter Notebooks. If you've used Jupyter Notebooks, raise your hands. All right. Okay, most people, Stephen, Justin, Josh, Friedrich, Devin, Cassie, Benjamin, Bart, and Ava. Okay. Thank you. So if you have used these before, homework 0 will be very, very quick and easy for you. If you have not, homework 0 presumes no prior experience. So this is just to get you registered, get you set up, and there will be directions for every other step through the way. Okay. Your second assignment is to start reading. We will be using SUMA in this class. So I posted on Canvas, paper by Clark et al. 2015. This paper ended up being so long, it's in part 1 and part 2. Both are up there, but for your reading assignment, I'm asking you just to read part 2, which actually goes through the actual equations that are in the model. This is a dense paper. So before you just start reading it and feeling overwhelmed, I've got directions on the assignment for which parts I want you to focus on. So make sure you read through the reading assignment first and then step through. At any point, if you have questions, please make notes and let me know. The goal is that by the end of the month, this model will make sense to you. And so the goal is for the class to answer your questions. So if the first time you read the paper, you're not sure about something, that's fine. Just let me know what it is. Okay. Then just the overview of all the logistics here. You probably are all ahead of me on this. So GoToMeeting is where we will have our lectures and our discussions. Canvas is where you can find all of the course-specific material and assignments. It's also where you'll turn your assignments in. HydroShare is a sharing location where all of the SUMA-specific models and forcing files will be located, and where you can save and share modules and forcing files, particularly if you need them for future work. GitHub offers a lot of services. All we will be using it for is a login authentication for the web-based computing. So you need to get a GitHub account. You do not have to be competent at using GitHub, which is good for me. Jupyter Notebooks is where you'll be modifying the SUMA options before you run it. Pangeo and the Google Cloud is where SUMA will actually run. The reason we are doing this is because installing this model locally on your computer has proven to be difficult for a lot of people. This is not a class on how to install things on your computer. It's a class on snow modeling. So the goal is to get you to snow modeling and the fun part as quickly as possible. And this is thank you to Bart and many others. And we'll have some more thank yous as we go further into that. Finally, everyone, please have a sense of humor. With all of these different types of technology, I'm sure something is going to go wrong somewhere along the way. Please just be patient with me and just let me know if any problems happen. All right, so are there any questions? Please type something into the chat box, even if it's, I have no questions now, none, just to make sure everybody can type in the chat box. Excellent. Looks good. Okay, so with that, I am going to move to the second module for today. And what we have here is a picture. Is it not working? What did I do? Did I stop sharing everything? Okay, it's lagged. Okay, so I need to be slow when I change a lot of things. All right, so what you see here is a picture of snow bridging logs. Matthew Sturm is a renowned snow scientist whose job it is to keep me honest, and he sends me photos quite frequently of things that my model does not represent well. One of those is snow bridging across logs, but it makes for a really cool picture. I think this is in his backyard. All right, so with that in mind, we don't do snow bridging across logs in most models. So essentially, all models are wrong, but some models are useful. This is a well-known quote by George E.P. Fox in his 1997 book. All right, so these are some slides from Bart Nyssen talking about what is a model. So if you look it up on Wikipedia, in general, a model is anything used in any way to represent anything else. More specific to this class, a model is a simplified or idealized description or conception of a particular system, situation, or process, often in mathematical terms, that is put forward as a basis for theoretical or empirical understanding, or for calculations, predictions, etc., a conceptual or mental representation of something, by the Oxford English Dictionary. So again, the things to focus are simplified, idealized conception. We generally are using our model to understand the real world. If our model is as complicated as the real world, we sometimes need a model to understand our model. It's often written in mathematical terms, and we use it for understanding or for calculations or predictions. So why would we even bother to model? The two main aims of any simulation model are to explore the implications of making certain assumptions about the nature of the real world system, or to predict the behavior of the real world system under a set of naturally occurring circumstances. This is from a paper by Keith Bevan. Again, the slide's from Bart. And our goals really are hypotheses, hence the earlier slide about developing multiple working hypotheses, which we can test through observation and experimentation. We can also use a model for exploration. And for many of us, we really want to understand in terms of prediction and forecasting. If we want to understand the system well enough that we can say what's going to happen in the future, or if some change happens, what do we expect? So this is a slide that shows a model really is like an onion. It starts with a computer code. With it, the computer code itself is very important, and part of the goal of this class will be to not treat that as a black box. Once you have the computer code, you set some parameters. You may tune these parameters. They may be hard-coded in the model. You will need to say an initial state. For snow, this is good. We can usually start in a state of no snow, but for other things, if you have a glacier, you have ice, you have soil, you need to start with some amount of water. And then you need some forcings. You need boundary conditions to your model, which in the case of snow are generally the meteorology. What's the precipitation, the temperature, the other variables that would cause snow to accumulate or melt. And we must think about all of these together to understand how the model works. And if something isn't working, it could be at any level of this model onion. Stages of a model simulation generally starts with a spin-up period. There's a model initial state where we say this is how much water, ice, snow we have in the model right now. And then there's a simulation period. This is, and then we simulate to some model state that we look at the output from our model. For seasonal snow, we have an easier case than in most situations with hydrology, and that we can generally start our model in the summer with 0 snow and move forward. Again, as I mentioned before, for glaciers and hydrology, we really need this spin-up period to figure out how much soil, water, or ice there is to start. We need to combine models with observations. The things we're going to go through in this class, starting next Monday, we'll talk about choosing the model architecture. What is in your model? How is it put together? How does it solve equations? Following that, we'll talk about developing parameterizations for the model. How do you specify the model parameters to go with those parameterizations? And we'll go into exactly what each of these are in just a few minutes. How do you pick the model forcings? How do you figure out if the model forcings are correct? And how do you evaluate your model and determine if it is functioning as you would like it to? There's a lot of different models when you think about any kind. The most straightforward and some of the earliest developed were data-driven models. These infer relationships from observations, often without attempting to describe the underlying causal processes. The most famous example in the world of snow hydrology is a regression model of maximum snow accumulation and summer stream flow. Other examples could be a stochastic time series model, like a weather generator, it just makes up the weather, or machine learning that predicts consumer preferences without trying to figure out how or why it's doing it. So for our snow model, this is a great paper that Bart found from 1953. This is from the United States Department of Agriculture, stream flow forecasting from snow surveys. And I really love the way they write because it reads like poetry. Winter snow quietly sifting down in remote forest places normally provides much of the life-giving water needed by thirsty western lands. The hum of power lines and the whirring wheels of industry reflect each melting flake. Busy municipalities absorb the runoff from melting snow. The works of man prosper and expand from nature's refrigerating cycle, water to snow to water. Snow minus heat stars far more water than any man-made reservoir ever conceived. Snow plus heat, together with rainfall, provides water for use by man. And here is the answer, that same paper, is that if you measure the maximum snow water equivalent in the western United States, you can predict the subsequent summer's runoff with fairly good accuracy. And this is still used by lots of different summer water use agricultural districts throughout the western US is a regression model, just like this. And here's a picture of the National Resource Conservation Service, which is part of the US Department of Agriculture. This is from the 1950s paper, and they are still in the same way with the same instruments going out and doing snow courses to get these key measurements each year. Along the same way, one of the earliest snow models developed for this application was Snow 17. How many people have heard of Snow 17? Can you click on your hand icon if you've heard of Snow 17? Maybe about a third of you have heard of it. All right. It's a conceptual model. It was developed by Eric Anderson, and it basically, it's a very well-developed model. It's what's called a temperature index model. It uses air temperature as the sole index to determine the energy exchange across the snow air interface. In addition to temperature, the only other input variable needed to run the model is precipitation. So the physical processes that take place within a snow cover are included in the model, but only in a simplified form. So here is a flow chart for the Snow 17 model. And basically, this one is pretty straightforward to understand. You feed it a time series of precipitation and temperature, the daily time step. Each time step, it says, is this rain or snow based on a temperature threshold? If it's snow, you accumulate snow cover. You then have energy exchange at the snow air interface. You keep track of how much heat deficit or cold content there is in the middle of the snow. You can have liquid water stored or passed through your snowpack. You can have ground melt your snowpack, and then you get water outflow at the bottom of your snow. And if it's rain, you can follow the other pathway where rain plus melt leads to snow cover outflow. And we'll go through some of the equations. So as we think about models, we have physically based models. And if you try to publish a paper these days, people will say, well, why aren't you using a physically based model? In reality, these are mostly physically motivated models. We are trying to represent causal relationships as much as possible through a direct description of the underlying physical processes. Examples could be a ballistics model. We know how something moves through the atmosphere. It could be the Richards equation for variably saturated flow to describe transport in the vadose zone. Again, how does water move through a porous medium? It could be the St. Venant equations for one-dimensional transient open channel flow. Again, we're trying to be as strict to the physics as we can be. However, in many cases with hydrology, we can't explain all of the physics of everything in the world. We often don't know what's happening under the ground. We often don't know the state of all the snow everywhere. And so the distinction in reality between a conceptual and a physically based model is not always clear cut and is often a function of scale, which is time and space, as you saw in Mark's diagram on the very, very first slide. So most models contain elements of all three approaches. We always are working with conceptual ideas of how things work. This is why, we always need to look at pictures. We need to look when we walk around the snow. When Matthew Sturm sends you something and says, is this in your model? And you say no, you might want to think about, should it be in my model? If it should be, how should I represent it? Data-driven, I've had some people tell me that, why you go out and try to collect data when, you could just model everything. Or never get away from needing data. And then physical equations, just trying to understand the physics better at all the time. All right, so this is the end of my second module. Before I go on to the third module, are there any comments or questions? People could type in the chat box or raise hands or unmute yourself and speak if you'd like to. Your favorite modes of communication. If we were in a classroom, I'd look at all your faces, but I feel like I'm in a vacuum. All right. Okay, so let's move on to decisions when building a model. This is our third and final module for today's class. This is based on Martin Clark's presentation about how and why he built the SUMA model, which is the one we will be using. So he gets credit for this. There's also slides from myself and Bart put in here. And this is a picture in New Zealand when Martin went out and measured the snowpack. Normally Martin writes models and doesn't get to measure the snowpack, and so this is one of his favorite photos. All right. So we're going to go through what are the pieces of a model. This is for modeling in general. And we're going to go through two simple examples here before we dive into all the details of a snow model. We'll talk about state variables, process parameterizations, model parameters, model forcing data, and numerical solution, how you identify which part is which and how they relate to each other. We'll then talk about physically motivated snow modeling. What are the major model development decisions that go into building a given snow model? Next week, we'll talk more about a variety of different snow models. And today, we're just going to talk about the motivation for the SUMA model. Then we'll talk about the impact of key model development decisions, the general philosophy underlying SUMA, and then a summary of what the research going forward from here. All right, so what are the ingredients of a model? So when you open the SUMA paper, you will see this figure. This is the art of modeling, right? You should always draw a picture of your model. I'm serious. It's very good to draw pictures of everything you do, even if you are a better or worse artist. Can somebody tell me which of the things in this picture do you think are most important to snow? Type in the chat box. So we've got snowfall. QSF is snowfall. That's probably number one. If you have no snowfall, you have no snow. That's absolutely right. The rainfall. Rain on snow is also important. The snow stored in the canopy is important. The snow state variable on the ground is important. The height of the vegetation is important. Is that right? Oh, that's a sensible heat within the vegetation, I think, is what people are voting for. How much the vegetation melts the snow. Take a picture back. Anything we can completely ignore here? The drainage from the aquifer, absolutely. I think we can probably, once it gets deep enough below the surface, we can neglect it in our snow modeling. But the one case we might want to be concerned about the aspects that are beneath the surface is in a case where we're trying to use stream flow to evaluate our snow model. If in this class, we'll just be doing point snow modeling, but if we are trying to integrate snow over entire basin into stream flow, then we need everything else. And that was part of the decision to teach everyone this model rather than one that is more developed only for snow, is because with this model, you have the capability of modeling all the way to stream flow, so you can check whether your snow model makes sense with stream flow at the bottom, in which case all of the subsurface flow also becomes more important. Okay, so within the picture, once we have a conceptual idea, and a picture really is a conceptual model, we need to define our state variables. So this is our storage of water and energy. And you can think about this from your basic fluid mechanics class or intro to physics classes, where we're applying just basic conservation of mass, conservation of energy, conservation of momentum. These all affect our state variables. And then we need the fluxes into and out what we're conserving that affect the evolution of those state variables. All right, so what do we mean by states and fluxes? So again, state variables represent storage. So they are something that is a state we need to track, that is stored in the system, and that will evolve over time. A state at some time t is a function of states at previous times. For example, our snow tomorrow depends on our snow today. This must include a model initial state. Okay, in the chat box, we've just typed some variables. Now type what you think the key state variables are in a snow model. You don't have to use the, you can just type right out what it is. You don't have to worry about the variables or shortcuts that were in the prior picture. So snow temperature and how that evolves through time is a state variable. Soil temperature is a state variable. Evolves through time. Liquid water content in the snowpack is a state variable. I haven't seen the absolute, maybe someone typed, sweet, Bart got it, yeah. There we go. Since I don't see all of them, yeah. Probably the most important is how much snow water equivalent do we have, right? How much snow is there to start with? Okay, so we've got the state variables representing the storage. So soil moisture is a state variable. Aspect likely would not be something that evolves over time. It wouldn't be, I mean, it would be a parameter likely for a location, because unless your snowpack is going to change slopes, which if you're doing avalanche modeling, maybe, but for most hydrology, hopefully it's not changing too much. But soil moisture will change, snow density will change. Okay, now our fluxes represent our exchange and transport, rate of flow of a property per unit area. So if you are thinking about drawing a control volume, this is what's coming into or out of your control volume. This only depends on quantities at time t. It does not depend on the prior time step. So the rate of change of a state variable is associated with one or more fluxes that are different from zero. All right, so again, in the chat box, type some examples of the key fluxes in a snow model. So we got sublimation and snowmelt, absolutely. So that's basically two ways snow comes out. Precipitation goes in, solar radiation is going to change our energy, snowfall is going to change our SWE, precip will change our liquid water content, absolutely. The liquid water flux through the snowpack, thermodynamic flux, melt water out of the snowpack. All are exactly right. They're all important fluxes. And soil moisture, again, soil moisture will be modeled in this model. There are some snow models that draw the line at the bottom of the snowpack and say I'm no longer modeling snow, it's soil moisture. Within the SUMA model, the vertical column goes all the way down to the soil moisture. And so the soil moisture is going to be a state variable rather than a flux, and it will change from flux out of the snowpack. Evapotranspiration will be a loss of water off the top. Latent and sensible heat flux will change the snow energy balance. Absolutely. Okay, so let's go back to similar to snow 17. Let's see if we can look at the ingredients of a snow model for a simple temperature index. snow model. So we start with our state equation. S is snow storage in millimeters, A is snow accumulation in millimeters per day, and M is snow melt in millimeters per day. So basically, a change in the state variable, ds dt, so change in snow storage per unit time equals snow accumulation minus snow melt, right? We've got two fluxes that change our state variable as a function of time. So here's our state variable. This is also known as a prognostic variable. These are our fluxes. Now, once we have our fluxes, we need to come up with some parameterizations and model parameters. So here, there's some more variables. So we've got P is precipitation rate in millimeters per day. TA is air temperature in Kelvin. Parameters kappa, melt factor in millimeters per day per Kelvin. And physical constants, TF, is our freezing point. So what we have here is makes logical sense. A, accumulation equals precipitation if the air temperature is less than some freezing point, and is equals 0. No snow will accumulate if the air temperature is greater than some freezing point. Our melt will be 0 if our air temperature is less than some freezing point. And melt will occur as some function of air temperature above that freezing point for air temperature greater than the freezing point. You can see our forcing data here, our precipitation and our air temperature. Our model parameter is kappa, and our physical constant, which could also be treated as a model parameter and is often changed quite a bit, of the freezing point for air. This type of analysis is quite easy to do for this model. It is a lot harder to do for a more complicated model, but if you are trying to detect a problem in your model, taking the time to write down what are all the state variables, what are all the fluxes, how are they parameterized, where did it come from, can really help you detect where an error might come from. So it's often worth just going to the drawing board and drawing out what are all the pieces of my model. In this case, the numerical solution is quite simple because the fluxes do not depend on the state variables. So the amount of snow melt is not going to change as a function of how much snow is already there in this particular model. The amount that snow accumulates also in this case is not going to depend on the snow that's already there. So you don't have to worry so much about your time step and your numerical solver for this simple model. So just to review, what is a prognostic and diagnostic equation or variable? The prognostic equation or variable at time t is dependent on values at previous times. A diagnostic equation or variable at time t is dependent only on values at time t. Okay, so just quickly type, is this a prognostic or a diagnostic equation here? Just type either P or D. Looks like we have a split. There's split votes here. Okay. All right. Here is here's our equation. So here looked like about half the class typed P for prognostic, about half the class typed D for diagnostic. So what we see in this equation is this is saying change in snow storage as a function of time is equal to accumulation minus melt. So the question is this equation depend on values at previous times? And I think the confusion arises because this change, the change itself does not depend on values at previous time. The change, because both accumulation and melt are just functions of right now, is dependent only. However, S is a prognostic variable. So the storage depends on values at prior times. So I think you're all correct. Either way you were thinking about it, as long as what I just said makes sense, I would say is a fair answer to that question. Does anyone have a question? Or is it that it's just sort of your interpretation of what I was asking? I think everybody's correct. All right, parameters and forcing. Parameters specify the shape of the function, and forcings are time-varying boundary conditions. So here again, our model parameter is something we might tune for a model or find the best value. Our air temperature, we're going to have a time series, it's our forcing data. And then our TF, our threshold, is another model parameter here. Parameterizations are basically ways we use parameters to try to get in between physics we understand and physics we don't understand. In many cases, we just have incomplete process knowledge of the underlying physics. And in other cases, we might know what we should do, but there's a big trade-off between physical realism and computational demand, or number of realizations. So rather than describe all the physical processes explicitly, we try to mimic the behavior of the system and its main causal relationships with the parameterization. It doesn't solve all our problems. In many cases, there's an incomplete knowledge of the parameters. Probably many of you have seen something like a temperature index snow model before, and those who've seen it have probably seen that this kappa value is different for almost every place it's applied. So there's no universal best value to be used in this equation at all places and times. So in the chat box, give an example of a pro or a con to parameterizing snowmelt based on air temperature. You can just write pro and then type something, or con and type something. So it ignores solar radiation and shading, definitely. It's a simplistic physical approximation. Con, it doesn't account for humidity. The pro is air temperature is a common measurement. Yeah, you can get a hold of that, or it's hard to get anything else. Any other thoughts? These are all good examples. And to this day, I think the snow community is split about the utility or lack thereof of a temperature index model. It's still in wide use. Okay, so this is also doesn't account for pre-existing saturation of the land surface. No, it doesn't. All right, so here's one that might. So here is a conceptual hydrology model. So here is, again, a simple model. This is a figure from Hornberg et al., Elements of Physical Hydrology. P is precipitation, ET is evapotranspiration, and R is runoff. Our state equation is ds dt, where here S is not snow storage, it's just water storage on the landscape. It equals precipitation, water in, minus evaporation, minus runoff, ways we can get water out. So we can diagnose this in the same way. So we've got state equation. So S here, soil storage, water stored on the landscape in millimeters. Our model forcing, P is the precipitation rate, millimeters per day. ET is evapotranspiration, millimeters per day. And Q is base flow in millimeters per day. And one thing I just want to note, again, when I said writing out your equations is useful if you're trying to check things, Always also writing out the units of everything is incredibly useful. I can't tell you how many times my model has not done what I wanted it to do, and it's because I got the units wrong somewhere. So just taking the time to write down what are all my variables and fluxes and what units are they in can help diagnose a lot of problems. So here is our state variable, our soil storage, our precipitation, that's our forcing data that we need to get from somewhere else. From a rain gauge or a meteorological model. And then our fluxes in this case are evapotranspiration and base flow or runoff. How do we parameterize those fluxes in our simple model? Again, we have some model forcing, which is E sub P, the potential ET rate. This is based often on temperature or solar radiation, how much energy is there available to transpire water from the system in millimeters per day. And then we have some cases here. So our amount of water transpired, if our storage is greater than or equal to some plant stress storage, if there's plenty of water, we will transpire at the potential rate. And if there is less water stored than some plant stress, then we will transpire at less than the potential rate. In this case, a ratio of the amount of water we have divided by the level of water that causes plant stress. The base flow is a function of the hydraulic conductivity, how fast water moves through the system, times, again, a ratio of the amount of soil water we have divided from some maximum soil water to some exponent. This is often referred to as a bucket model. How full is your bucket? How fast is it going to run off? The thing you'll notice in these equations that make them very different from the simple snow model is, again, here are, as I just went through, our model parameters. There's a number of them, our forcing data, and then our state variable. This is what shows up as different, is that in this case, our state variable shows up in both of our fluxes. The manner in which we are able to change the water stored on the landscape depends on the water that is there right now. So our model fluxes depend on our state variables. So whereas before, even though S was a prognostic variable, dSdt was a diagnostic equation, we now have a prognostic equation. Your change depends on where you are. This means your time step can matter a lot. And Martin Clark wrote a couple papers talking about this and calling them numerical demons because they come to haunt you. Are there any questions so far? I'm gonna look for hands. Seeing hands. Everybody's okay or went completely to sleep? Okay. All right. So we have all the components. How do we pull it together? Here's the picture from the beginning. We have a general modeling problem. So in the construction of the SUMA model, Martin's basic ideas were that most hydrologic modelers actually agree about where the dominant fluxes of water and energy come from and how they affect the time evolution of the thermodynamic and hydrologic states. I don't think you could find any snow or hydrology model anywhere that wouldn't say precipitation and snowfall was very important, right? We agree. Most people would draw this picture with similar arrows and labels, even if they might make their trees different sizes. The collective understanding of the connectivity of state variables and fluxes allows us to formulate general governing model equations for different subdomains. So we could write the things we all agree on to run the core of the model. These governing equations, conservation of mass, conservation of energy, are scale invariant. And thus the key modeling decisions wherein people doing modeling disagree relate to the spatial discretization of the model domain. For example, are you going to do a lumped model over your entire basin? Do you want different grid cells everywhere? The approaches used to parameterize individual fluxes. How do you think that water percolates through the snowpack? and the methods used to solve the governing model equations. How do you actually code time stepping within your model? So given this, it's possible to develop a unified model framework, and the goal of SUMA is to come up with a single set of governing equations with the capability to use both different spatial discretizations, different flux parameterizations and model parameters, and different time stepping schemes. So, so what are some of the major decisions with that? So here's a picture. This is again in New Zealand. How should we, what would you say if we wanted to just model snow on this hill slope? Looking at this picture, type in the chat box some of the dominant snow processes in this environment. Solar radiation definitely looks like a sunny day. Wind transport, looks like it's a windy spot. Precipitation, shading, aspect, slope. The direction the slope's facing is going to relate to your solar radiation. Snow sublimation, yeah, if it's sunny and windy, that's going to happen a lot. Temperature, it'll determine whether that snow's melting or not. And humidity, Avalanches, it definitely looks like prone for avalanche terrain. That could redistribute the snow quite a bit. So albedo is going to matter for the solar radiation. So some of the things Martin came up with is in this terrain, drifting and avalanching are going to be very important to where there's snow on the ground. There's very non-homogeneous or variable precipitation across the landscape. This is within the rain-snow transition, so that temperature, is it rain, is it snow? The net energy flux for the snowpack, people brought up ideas of solar radiation, albedo, what's the aspect of the slope? Meltwater flow, how will water that melts percolate through the snowpack, where is it going? If we're interested in avalanching here, changes in snow properties, grain growth, snow compaction are going to be very important. If we want to simulate all of these processes, what information are we going to need? We're going to need a good idea about the meteorology of this region. We need to know the precipitation, the temperature, wind, humidity. You guys had a lot of these shortwave and longwave radiation. Air pressure, less important, but we need at least a rough idea of it. We're also going to have some model parameters. Drifting is something we're not very good at modeling, so we're going to need to estimate it. Snow albedo, again, we're not so good at physically based modeling, so we often parameterize it. Turbulent heat fluxes, another very difficult physical problem, so we often parameterize that. And then storage and transmission of liquid water in the snowpack are also hard to numerically represent, so we often come up with what we consider reasonable guesses for all of these parameters using parameterizations. Okay, so now this is a starting point. We will be going through, I'm going to show you some equations. We will be going through the details throughout the rest of the course. But to get all this, to describe the temporal evolution of the thermodynamic and hydrologic states, we need some equations of thermodynamics. We need our model to be able to handle the change in temperature with each time step, the melt or freeze of liquid and solid components of our snowpack, and the fluxes of energy at the boundaries. We'll need this for each layer that we choose to represent in our snowpack. We also need to track the conservation equations for hydrology. So we'll need the volumetric liquid water content, where we need to go through the change in liquid water within the snowpack at each time step, which will increase as snow melts, ice component melts, and will decrease as liquid water freezes. This will also be a function of fluxes at the boundaries, which include liquid water coming in through the top, moving out through the bottom, as well as any evaporation if there's liquid water near the surface that's evaporating to the sky. We also need to keep track of our volumetric ice content, with each time step, we'll have a change in ice content with each unit time. That change in ice will change as a function of melting or freezing. If liquid water freezes, our ice content goes up. If ice melts, our ice content goes down. Our volumetric ice content will change as our snow is compacted. We'll have different densities of that ice. And then we can have fluxes at the boundaries. We can have more snow and ice on the top, and we can have sublimation of ice component leaving. Within the SUMA model, the snow of itself, and we will talk on Monday about the snow structure and the details of these parts, is represented as a fractional component of ice, liquid, and air, so that we can keep track with these basic equations, each component. There are some other models, like our very simple one, there's just snow water equivalent, and we don't worry about which parts are frozen and liquid as explicitly as you see here. Some notes about this model is that the fluxes are only defined in the vertical dimension. So there's no lateral exchange of water and energy among the elements in this snow model. So they're isolated vertical columns. This simplifies the numerics. Within this class, we will be doing point snow modeling. There are other cases where it's obvious, again, if you wanted avalanche redistribution, where you might want something else. Spatial variability can be represented through spatial variability in the model forcing. For example, you can change how much precipitation you put on different point models of snow, and you can change spatial variability in the radiation. You could also change model parameters with space, such as have more dust in one location. However, these basic equations, if you will not move water from an upper layer in the snowpack in one location to a lower layer in the snowpack in another location, the water will go straight down in the snowpack. Most snow models follow these basic governing equations with different forms. So if we have this basic equation, we then need to think about our spatial discretization of the model domain, and we'll be getting to this in a couple weeks. You might want to think about the size and shape of the model elements. A lot of people like to just draw a grid and say, okay, if we've got a little vertical snowpack, we'll do it in each square on the landscape. This is similar to what's done in the DHSVM model, if you've heard of that. We also have choices in our vertical discretization of each model element. How many layers do we want in the snowpack? How thick do we want those layers? When do we want the snow to change to have more layers or fewer layers? There's a lot of variability in how different models handle this. We'll be talking about this quite a bit on Monday. Also, the parameterization of the model fluxes and the properties. How do you spatially distribute the forcing data? We're talking about that next Wednesday. What are your vertical flux parameterizations for connectivity within the layers you put in your snow model? What is your surface fluxes? Your forcing at the surface is going to be a function of your net short wave, net long wave, and your sensible and latent heat flux, as well as any energy and precipitation. How do you define conductivity within your snowpack? If each of your layers of the snowpack have a state variable of that snowpack's temperature, how does that temperature move throughout the snowpack as a function of height and time? And some of the questions that are very common when we think about net shortwave: how do we represent snow albedo? How do we represent atmospheric stability? We'll be talking about this explicitly. How do we represent thermal conductivity? We need to specify the model parameters. For example, if we use this parameterization for snow albedo, we have to come up with how much snow is necessary to refresh the albedo. So this is a change in albedo per unit time. is a function of the albedo, maximum snow albedo minus the minimum snow albedo, that when there's some key amount of new snowfall, we refresh to the maximum. But how much new snowfall counts? Once you have new snowfall, how quickly does it decay to a lower albedo? What's your albedo decay rate? And then what is the minimum albedo that your snow can go to? Does it decay all the way down to a very low albedo so it looks quite dark? Do you think there's dust in it that goes quite dark? Do you think it's still fairly bright? How do you come up with these parameters in your model? And finally, how are you going to time step your model forward? For example, we talked about, you can imagine your snowpack, and we'll talk about this more on Monday. Your snowpack has water percolating through layers of different temperatures. Should the water freeze at each spot, and if the water freezes somewhere, it's going to change the temperature of that layer. It's difficult to solve all of the equations we just showed simultaneously, particularly for a number of layers in a model. So most models follow a solution sequence. How do you decide what order you advance each step in the model? Do you adopt an iterative solution procedure? So many fluxes are a nonlinear function of the model states. So iterative methods typically are used to estimate the state at the end of the time step. This is a key of, if you're changing something, you're going to want to make a step to change the variable and then use the new state variable to check what should the step be. There's a lot of different variations within how this is implemented in models, and we'll talk more about this. And then how do you check for numerical errors? Do you monitor errors in your iterative procedure and do adaptive substepping? For example, you might need to advance forward smaller time steps to improve the efficiency. If things are changing very, very rapidly, you want to take smaller time steps in your model, but you might not want your model to run at a very small time step all of the time because your computer will get tired. You may also want to reduce temporal truncation errors. This has also been a problem that most people who don't think more about the physics and the science and less about the actual modeling, is that you can run the same snow model on two different computers and get different answers just due to how different computers truncate errors. You'll get slightly different answers. And so it can be hard to recreate results because of some of these time stepping issues. So this is the general philosophy underlying SUMA. The objectives were to create a unified approach to hydrologic modeling. That's the reason we're using this model, is because you have a way to actually test different hypotheses about how a model should be put together. It's put together careful to improve model fidelity, which means that all the time stepping schemes were checked carefully, to better characterize model uncertainty, because you can compare different model choices within one framework. Hopefully through in this framework, you can try out different ideas side by side to better understand model weaknesses and accelerate model development. Problem with using a lot of different models is that when you run a model intercomparison experiment, and we'll read a paper of one of the early intercomparison experiments later in this class, there were so many differences among all the participating models that it's pretty much impossible to figure out which difference was due to what. It was due to so many differences in model equations that the end result was, yes, models are different. We still don't know what's a good model and what's not. Leads to a poor understanding of model limitations, in that most models are not constructed to enable a controlled and systematic approach to model development and improvement. And different models are developed for different disciplines. And so we need a framework where people can work together. Again, for example, most hydrology models don't represent biophysical processes very well. Again, we went through this. And the goal is, rather than have one favorite model, you can put forward a lot of different combinations of model And then you might actually, rather than just saying you love one child better than another, you can say, you know, this child is behaving better in this situation. And think about numerical modeling as a subjective decision-making processes. Again, some decisions can be based on relatively well understood physical principles. For example, can we explicitly simulate snow surface energy exchanges rather than simulating melt just as an empirical function of temperature? Whereas other modeling decisions are much more ambiguous. For example, saturation excess runoff. If you've seen water on the top of the snow, you know, what should you do with that in your model? Or macropore flow. If it rains really heavy, you may have seen channels where water goes through really fast. Is it significant? Is it dominant? If it's important, how do we put it in a model? We honestly don't know most places what's happening under the bedrock. Is bedrock permeable? What happens to subsurface water, places we can't see? And then some modeling decisions are just pragmatic, based on the computer budget or other considerations. For example, you know, even if we have a LiDAR map of snow depth at 1 meter resolution, does it make sense to run your model at 1 meter resolution, or is there some way to represent that more compactly? Also, with the transmission of shortwave radiation through a canopy, can we use a simple equation, or do we need a very sophisticated radiation balance? So as we're nearing the end here, this you will see in the paper. This was what Martin calls his horrendogram. It's how he has organized the SUMA model. Starts with a solver and the state variables in the center. Starts with the physics that are very well understood as governing equations about how each of these state variables change in space and time. And then outside it has a lot of different options where you can put in different ways that different models have parameterized different factors. And so we'll be going through some of these over the next weeks. So in summary, the objectives were to give a more precise representation of model uncertainty in a solid framework, give a detailed evaluation competing modeling approaches so that you could use this as a modeling template to try to reconstruct existing modeling approaches. You could make SUMA act like your favorite model, or you could use it to derive a new modeling methodology and directly compare it to something already existing to see if it does better, thus providing a systematic and controlled approach to model and evaluation. This gives guidance for future model development. Personally, even if we're using another model, we often use this model to check that model or to check a couple options of something we see might be a problem in the model we want to use. And then to use improved understanding of impact of different decisions, and thus just improving any type of process model in general. So homework model exercises, we'll use SUMA, and the first reading is the paper on this framework. And are there any questions? Here are the people heli skiing down this mountain we looked at in New Zealand. No questions? There's a heli drop. There's the volunteers. Do you want to volunteer? Anybody? So this is Martin's favorite quote. I'm sure this is exactly what he was thinking while he was skiing down this path right here. All right, one volunteer. That's good. Snow modeling field trip to New Zealand. All right. All right, so if there are no questions now, please do go on to the Canvas site. You should have access to all three of these modules in both PowerPoint and PDF forms. If you want to look at anything, click on any of the links. You should also at some point have an exciting video of this talk recorded. And if you have any questions, just post them in the discussion board there, as well as posting about who you are. And we will meet back in virtual land on Monday the 8th. So thank you and goodbye. Now, how do I leave? Am I not sharing? Video. Video, I'm not sharing. Yeah. Okay. And all right. You still hear me? Did Liz say I was supposed to stop it? I'll just exit. Continue. What am I reading?